All right, so second set of trig integrals, I like to give you a choice, usually between something where we need to do power reducing and something where we need our secant and tangent. Or even, I guess I could do the ones that require that, like sum to difference, gross. I tend not to do that. If I did, I would give you the formulas, and that seems to make it just a pretty straightforward and easy question that's not really worth it. So that's why I stick with these two. So first and foremost, anytime we have only even powers of sine and cosine, we are kind of screwed. We need to use that power reducing formula. Our power reducing formula comes from our double angle identities, which you will have, but you will have to rearrange if you want. So this one, we know that cosine squared of x is equal to 1 plus cosine of 2x over 2. So we're going to go ahead and rewrite this as 1 plus cosine of 2x over 2 squared. All right, now I'm going to head pull the 1/4 multiple of that scalar multiplier in front. We'd have to do the distribution in the numerator, so we're going to have 1 plus 2 cosine of 2x plus cosine squared of 2x. So right now, this is good. We could take the antiderivative of both 1 and 2 cosine 2x. We are still looking sad here because we have another even power of cosine. And this is the beauty of the power reducing. It just keeps giving. And so you could go ahead, split this into separate integrals and evaluate or take the antiderivative of just one of them now. I personally am just going to keep messing with my integrand until I can finally rewrite it and take my antiderivative. So I'm going to go ahead, leave the 1 and the 2 cosine, even though I know I could take cosine of 2x, the antiderivatives. I'm just going to leave them there. And then plus, we have another, 1 plus cosine of 2x over 2 dx. Whoop, whoop. All right. Can't really pull that 1/2 out in front. If I wanted to, though, I could at least combine some like terms, make my work a little bit less hellish here. Let's see. I'm going to have a 1 plus a 1/2, so we'll have a 3/2 for our constant up in here. I'll highlight those so that's more obvious. 1 and the 1/2 add together to give me 3/2. Cute. And turns out, let's go ahead and use a different color. Come on, you can do it. Cosine of 2x and cosine of 2x here are both also looking like we can add those together because we have like terms. So I have 2 cosine of 2x plus a 1/2 of a cosine of 2x. So we'll end up with a plus 5/2 cosine of 2x. And now if I wanted to, pulling that extra 1/2 out in front doesn't feel quite as gross as it did before. And I could have before, and we'll look at what that would have looked like. So I'm going to make this a 1/8 3 plus 5 cosine of 2x dx. So if I had been like, I want to get rid of that 1/2, I would have needed to divide out 1/2 from 2, which would have left me with 4. 4 plus 1 is 5. And I would have needed to divide out from 1, that 1/2, which would have left me with 2, and 2 plus 1 is 3. So we could have gotten there if I wanted to go ahead and bring that 1/2 out in front of the integral earlier. Just making sure that I realize if I pull something in front of the integral, it needs to come out in front of the integral for everything. But you can see here, I'm probably not going to make any mistakes in terms of distributing stuff. So let's go ahead. We are now at a point where we can take an antiderivative. The 1/8 will stay. We're going to have a 3x. And then cosine will become sine. Since we have a 2, we're going to have to divide by that 2. And then we stay positive. So boop. That's it. If you want to clean it up more, feel free, but you are not obligated to. I'm completely okay with this as your final answer. Oh my God, I did not leave myself much space for that second question, but let's try it. All right, so let's try the second one here. This is all about peeling off secants or secants or tangents. Again, I like to think of these questions. The first one, the power reducing, We just have to recognize the even powers. We're kind of screwed. Power reducing is helpful. For secant and tangent, we want to do what we did with sine and cosine, except for that our derivatives for secant and tangent are a little bit weirder, right? We're looking to either set our du equal to secant squared of x. Oops, come on. I like wanted to write theta because I'm just like in such a trig sub mood. Or our du equal to secant x tan x, because those are the two derivatives of tangent and secant respectively, right? So we want to look for those. The latter one here would kind of screw us, right? If I pull out one secant and one tangent factor here, I'm going to be left with odd powers on both secant and tangent, which means I can't leverage my Pythag identities to make one of those things disappear. So that's not the business. We're going to go, oops, that doesn't seem good. However, pulling out a secant squared in this particular case is going to serve us, right? Because that'll leave me with an even number of secants, which I can then rewrite as tangent, the thing I need to be able to do my u sub. Again, this is not always going to work, right? We've seen things before like tangent squared and tangent to the fourth where we don't have any secant squares to do this with. In those situations, we can convert our tangent to secant squared plus 1, and it usually saves us all by itself because secant is kind of lovely that way. So let's go ahead and do this. So we're going to leave this as a secant squared x tan to the 6x dx. And I'm going to go ahead and throw the other secant squared x right next to my dx because that's the goal, right? This is why we did this. This whole thing is going to become du. And if that's true, our u had to have been tangent of x, right? And we have our tangent of x here. If only we could rewrite secant of x. Oh, wait, but we can. Right? We can definitely do that. And this is where I'm like, ugh. Okay, if I divide everything by cosine squared. All right, so that's going to be 1, tangent squared plus 1 is equal to secant squared. All right, so secant squared is tangent squared plus 1. All right, I just had to do that because my brain doesn't have these things memorized. Judge me all you want. Tangent squared x plus 1 is what this thing is equal to. And then we have our tangent to the 6x, and we have our secant squared. I can erase all of my Pythag identity work off to the side. One day I'll memorize. I will not. I refuse. It's just too easy to get the other ones for free with knowing just one of them. So I refuse to memorize it. All right, so now we're cooking, right? We've got everything in terms of tangent. I can go ahead and do my u sub now. We have u squared plus 1. Dang, I was way too nice last semester because we still don't have to do any distribution. I'll think about that as I write my tests this year. And so now we're at u to the 8th plus u to the 6th du. So we have, I'm just going to go ahead and do the substitution back. We have tangent to the 9th over 9 plus tangent to the 7th over 7 plus c, all of that, tangent of x, right? Cute. So those are your two options for 6. I really do want to push us to a little further than just powers of sine and cosine that have an odd that we can peel off. So I tend to stick with these two concepts, that power reducing, our secant tangent stuff. But no, I think that whichever one is harder really just depends on which one you felt more comfortable with in the take home. So I don't think there's any usual level of difficulty difference between these two problems.